Welcome to the TimeWeaver product demo. For this demonstration I've selected also the Infineon Tricore AURIX architecture, and we would like to start from scratch again, setting up a first analysis project. For that, in the first step we have to select an executable program again, and let's select our famous scenarios acube.elf file like we did in the AIT product demo. Next step is a basic configuration in the I specification file, which I have prepared here. It's called the scenarios acube ICE file, and as previously we have just a compiler specification here, which you can also generate interactively via the insert ICE annotation context menu and compiler. And then you can select the corresponding compiler that has been used to produce your binary. In this case it was the GCC, right? Alright, then we have a context specification which basically decides how precise the underlying value analysis will operate. And we have a hardware description where we find for instance, the clock rate annotation like this one here, which is 100 megahertz in this example, and the remaining parts of that hardware ICE annotation file we do not really need, since we do a TimeWeaver hybrid analysis where we rely on the instruction traces. Okay, next step, configuring the hardware, is also not necessary in case of TimeWeaver. Since again we rely on the instruction level timings coming from the traces. But what we need actually is, in addition to the ELF binary, of course, a set of trace files. In my case, I have produced the instruction level traces by the by the Lauterbach debugger. It's the ASCII in the ASCII format, and it's can be found here. It's the scenarios acube text.gsc file. It has been compressed with gzip. That is my only trace file input. We could of course also provide some more traces here if you have them. Alright, next step is, as usual, we should save our analysis project, and there is one already prepared, so let's overwrite that one. Now that we have stored the project file with the APX extension, which contains references to the binaries, the configuration files, the input trace files, the absolute paths have been replaced to relative paths relative to the APX project location. Okay, next thing is we can provide an entry point for the TimeWeaver analysis. So for that we switch to Analysis, Create, TimeWeaver, and generate a new or create a new analysis item, which is initially called TimeWeaver. And here in this area we can select the entry point where we want to start from, and by clicking on this pipette symbol, again, all entries from the symbol table will be extracted out of the binary. And in contrast to the AT analysis, you can now filter that list by all analysis items that, or analysis entries that are shown in the trace files. So by clicking on that, we will be sure that the selected entry point can be a valid entry point for TimeWeaver analysis. So let's filter the list by the task, and we will find our famous 10 millisecond task entry point. Before we start the analysis, let's take that start again as the ID, put a suffix like TimeWeaver behind, and save the project again before we start the analysis. Now that we have specified all inputs, we are ready to start the analysis. As usual, by clicking on the fast forward button, you would start the analysis of all entries here in the list. Currently we just have one, and by clicking or by selecting the item first and clicking on play button or the play interactive, only the selected analysis item will be executed. So let's start that one here via the play button. And you will see the individual analysis steps. Again, first the call and control flow reconstruction and the static value analysis will be performed on starting with that entry point here with this routine. And then the path analysis step, which also executes the trace parsing and prepares the path, the worst case path finding, will be executed. And this also, by the way, gives some information about how many trace snippets for this task could be extracted. In this case, it was just 15 individual executions of the very same task, the 10 millisecond task. We call that trace snippets that could be extracted from the traces, from the trace execution. All right, and then the result is computed. The worst case execution time estimate in this case is 102.19 microseconds. And again, like in the IT analyzer, you can visualize that result in the call and control flow visualization. This looks like this. Here again, you have the resulting information about this 102.19 microseconds, and then we have a trace statistics. Again, these 15 trace snippets, which were identified in the trace input files. And a nice additional information is that the minimum trace time, so the minimum execution time observed overall 15 trace executions of the same task, was just 96.81 microseconds. The maximum observed trace time, the maximum observed execution time in these 15 executions was just 100.98 microseconds. But the worst case execution time estimate was even higher than the maximum, which is 102.19 microseconds, because of loop upscaling and worst case execution time extrapolation, which I explained in the presentation. Then there's some average trace time information and some standard deviation information as well. Below, you'll find the call graph with the timing contribution of each routine, very similar to what we have seen from the AIT tool. So we have a contribution, timing contribution here of each individual routine with the visualization here in these colored bars. So these red bars indicate the contribution of the routine to the entire worst case timing. And the orange bar indicates the so-called cumulative part, basically the contributions of each of the children routines. So on the first view, you can see that the string copy X here contributes almost half to the entire worst case execution time. The mem copy also contributes a lot in the string copy, and this is because those three have some loops in it that have a high iteration count, which we will see later. Like in AIT, you can also investigate the control flow graph of the individual routines. So for instance, if we dive into the proc1, we see that this is the worst case path in the control flow of protein proc1. And after each of such a basic block, where we visualize the C code information, if this is available, if the binary was compiled with 12 debug info, and if the sources could be found, we also visualize the corresponding C code. Otherwise, you can also, of course, have a look to the machine instructions here. After such a basic block, you will always find a timing node that shows how often this basic block was executed on the worst case, in this case just once, and what was the observed maximum timing for that basic block, in this case just 39 cycles overall of these 15 trace snippets. So this tau, this is not a T, this is a tau symbol, indicates how much trace snippets were available, or how much timing information could be extracted out of the trace data for this basic block here. And so on. Then the routine call memcopyx is called, which you can follow as we have seen before. And then we execute this basic block here, which takes 128 bytes in the worst case, in the maximum. And here we have an if then else again, like in the AT case. The value analysis, however, could prove that we have a certain dead code situation here. So this else branch could never be executed, since this condition here is always true, right? And then the static value analyzer could prove that you always have to take the then case for the worst case. If this was not the case, that the value analyzer could exclude the else branch, then again the path analysis would have selected the branch which leads to the overall global worst case. We also have a nice statistics overview in case of TimeWeaver here. And this statistics is a bit extended compared to the IT tool. First, we have the same WCET estimate contribution list. So that means it lists all the functions and loops and how much cycles, how is the self-contribution of each routine and loop, and cumulative execution again. So you might sort for the self-contribution here and directly see that, for instance, these three loops contribute most to the entire worst-case execution time. So there's kind of feedback for optimization here available as well. The same information is available context-specific, where you can see how the contribution is depending on the corresponding call context. So for instance, 10 millisecond entry function calls try at a certain address, then the proc0 is called at a certain address, and proc0 calls here several more routines, like the string copy, for instance, twice, and we have a different timing behavior depending on the call scenario. And this will be distinguished here in TimeWeaver as well. So we have a context-specific worst-case timing extraction from the traces and combination to find the worst-case path. The loop-bound view is a bit extended because we no longer have just the analytically values that has been determined by the worst case, the static worst case loop analysis. So this would be the column min and max here, what the loop analysis has found out as bounds. We also have an information about how often these loops are executed in the trace execution, and what finally has been selected for the worst case calculation. In the optimal case, the trace maxes correspond or are equal to the analytically determined max bound. But if the trace max is lower than the analytically determined bound by the static analyzer, we perform this loop upscaling, which I mentioned before. So that means that the timing contribution of one loop body execution will be scaled up to the amount or the numbers of these max coming from the static analysis. Then we have variable usage information. So again, the value analysis provides information which global variable has been executed, has been accessed, how often, so how often it was read and written on the worst case path, also context specific. And in addition to these information, we of course also give some feedback about the trace quality. The first thing is the trace segments view. So we provide an overview about the time variance for each of the trace segments. The trace segments are basically these basic blocks which you have seen. So we get a timestamp for each basic block. And for instance, since we have an entire execution of the entire task, 15 times here, we have of course also at least 15 different timestamps for each of these basic blocks, and you see here some kind of variance. So for instance, if you go to this basic block here, let's say this one here, we can double click on it, and we have 15 timestamps. 14 of them are quite fast So 9 cycles, 9, 9, so they are all 9, but the very first one took a lot of time, more than 28 cycles, and of course for the worst case we took that 28 cycles as an effective max. And we do that for each of these segments. In addition to that view, we also have what we call a trace coverage view, and this indicates how your trace quality is. So if all your routines and instructions have really been covered in your trace execution. If there are some parts missing, then you should extend your test settings, your test scenarios to cover also the missing instructions, right? In this example, I have an ideal case, a benchmark program where all the code parts are executed in a row. So we have full coverage here, 100% in every function. And this trace coverage is also available now, context specific. So we have seen the string copy was executed in several contexts, so we have the information also context specific. Let me give you some idea how the trace coverage could look like if you have not full coverage. For that, I'm just executing the 5 millisecond task here as well, because the 5 millisecond task is quite interesting. It shows the following. So first of all, in the graph, you directly see that some part of the call graph is missing in the trace. So because these routines are surrounded by a red border here. And if you go inside of the entry function, you also see the reason why this is the case. So initially you have some if condition, and the signal I think is coming from the outside. But in every of these 15 trace measurements, always the else branch was observed, was executed, where the BS math index was set to 20, and it was never set to the case that the BS math index became 10. And later, when you check the BS math index, of course, since it was never 10, we would never enter the BS case where we call the BS function. So also on control flow graph level, we indicate which which code parts have not been covered by the measurements. Here in this case, of course, we were always entering the BS math index equals 20 case and called the math routine. And the branch around it is not covered. And this information can also be seen in the statistics view. If you open the statistics view and the trace coverage, you see that now that BS has here 0% coverage, and inside of the entry function we have just 75% of all blocks traced, and 78% of all instructions. So this could give an indication that your test scenarios are not yet sufficiently high, and you should have a look how you could change your test settings to also trigger the case that the signal here becomes true, and the BS math index is set to 10 in the consequence. Okay. There are many more features in TimeWeaver, and I can only mention a few more. For instance, we have here under output a very detailed reporting mechanism, so we can produce textual report files for the analysis we have taken here, and this looks like this. There's an overview about the settings we have done, statistics, value analysis statistics, and of course also the timing contributions in a tabular format, like here. You will find several categories you can browse to. The same information will be written or can be written to an XML file format for a better automatic post-processing, and also of course into the HTML file for a very compact overview like this. Here you see that which version has been used to perform this analysis here. This is the result, the worst case execution time estimate, and the contribution table, so how much every routine and loop contributes to the overall timing. And last but not least, an overview about remaining warnings and errors in that analysis. Yes, what can also be set is, of course, here local specifications. You can pre-select several trace snippets, especially not to take all the 15 which are available in the trace file, but only selected ones, mainly for debugging purposes. The trace core ID is usually determined automatically, and you can set a so-called cumulative frequency filter. So you can skip certain timestamps which are lying beyond a border, and so for instance, exceptional outliers which you would like to filter out. And last, you can set an expected result. For instance, in this case, you could say we have allocated 200 microseconds for that task, and since 184 are below, everything is nice, but if the time later, the worst case execution time increases then and exceeds the expected result, you will get an assertion violation that you can monitor continuously. Before I come to an end of my demo, I would like to show you at least one more example, namely a multi-core example. For that, let me open another prepared example. It's called Multicore Project Example, and it comes with 3 prepared tasks. Task 1, task 2, and a toggle task. And well, this looks like this. So by the way, we have here some ELF binary again, and are reading in some trace file here. And if we have a look to the source code, I can give you an overview on how these what is computed actually inside of this very trivial task. So the task 1 is basically doing the following. It waits for some synchronization. So task 1 is running on core 0, task 2 is running on core 1, and the toggle task is also running on a third separate core. So as I said, task 1 waits for some synchronization and then performs some computation. The computation is very straightforward. It just increments a loop from 0 to 50 here, or 49, and increments a global resource sum by the index I. And the wait for sync is just implemented by a simple while loop, waiting that a certain bit toggles. Yes, and the task 2 is similar. It waits for also some synchronization, and this time it waits for the opposite toggle of that bit, and performs another computation, namely it decrements the sum variable again by the index. The toggle task itself is also very simple. If the toggle equals to 1 is true, then it sets it to 0. Otherwise, it enables it to 1. And now the question is how often these tasks are executed. Task 1 and task 2 are infinitely often scheduled on each of the cores, and the toggle task is run on a random basis, so that the toggling takes longer or less time, depending on to simulate that, depending on some outside situation. So what happens now in the worst case execution time analysis of task 1 and task 2? Let's see that. So for that, we can run these 2 tasks concurrently by clicking on this fast forward button. And so both task 1 and task 2 are executed in parallel. So all the steps performed for TimeWeaver analysis will be done concurrently. And we end up with a worst case execution time bound of 180 microseconds for task 1 and 157.91 microseconds for the task 2. Let's have a deeper look on the visualization of task 1. Here we have some more interesting information. So we have basically seen 899 different executions of that was task 1 in the trace files. So we have 899 trace snippets extracted. The minimum observed trace time was just 27.97 microseconds for a trivial execution scenario where we certainly did not wait for sync at all, and the bit was already or toggled so that we could proceed with the compute 1 execution. And we have also a maximum observed trace time of 131 microseconds. The worst case bound, however, is 180, since we do extrapolation and recombine individual timings for the trace segments to find an overall worst case timing scenario, right? So one important difference to the IT, to the static approach, is here that this waiting for this bit toggle, which is basically a blocking that is caused by the toggle task running on a different core, and waiting until this toggle task has finished. This waiting would not have been bounded in the static analysis, and the user would have been asked by providing a worst case iteration count or worst case timing for that wait loop. But in this case, this information could be extracted out of the trace data, out of these 899 trace snippets. And you can see that quite interestingly also in the trace segments view. If we have a view to the total view, we see that we have 899 extracted trace snippets, and most of them are producing a low execution time, like, let me wait here, with 28 microseconds, or we've seen the minimum was lying at 27. This is, as I assumed, the case when we do not actually wait for synchronization. We can directly proceed with performing compute 1. But if we have to wait for synchronization, it basically depends on how long the toggle task, or how long it takes until the toggle task is executed again. And we have a certain randomization implemented here, and it can wait differently long. And the worst case wait scenario is reached in these snippets here. And here we basically reach then these 131 for the individual snippets. Yeah? So then here you can really nicely see the different snippets and the distribution of these timestamps over these 899 snippets. You can also get a different view here, for instance, the polar view, or we also, and here you see certain accumulation here, and there's also distribution, survival graph that also indicates where is our average cycles reached, like in this case, which is 52 microseconds, and around that average we have a standard deviation, of course. Similar information can be seen, of course, also in the task 2, where we have the opposite waiting behavior, right? But it looks very similar. All right, this concludes my demo on TimeWeaver. If you have more questions to that analysis solution, to the hybrid worst case execution time analyzer, please feel free to contact us via info@absint.com or have a look to our website. Thank you very much for your interest. Take care and bye-bye.